In this second video, we will look at the ionization energy and the trend in the ionization energy as we go across period 3. This will be a revision of what we covered in term 1, so there shouldn't be any concepts that's new to you. And then we're also going to look very briefly at ceramics. We're going to look at the properties of some ceramics and then explain that in terms of the bonding and structure of the different compounds. Before we look at the trends going across period 3, just a quick look at the definition of ionization energy gain. It is an important one. So it is the amount of energy required to remove 1 mole of electrons. It's important to specify that amount. Remove 1 mole of electrons from 1 mole of atoms or ions. And it is also very important to specify that the atoms or ions are in the gas phase. And then they often ask you to write an equation to show either the first or the second or the third ionization energy of a particular element. And depending on what they ask, if it is first ionization energy, we'll start with an atom. And it's important to show that it's in the gas phase. So here, these state symbols are incredibly important. You must show a little G for gas phase. So we start with the atom in the gas phase. We go to the ion in the gas phase with a 1+ charge because we have removed 1 electron. If they ask for second ionization energy, then we start with ions with a charge of 1+, again in the gas phase, remove 1 electron from each of those ions, 1 mole of those ions to form ions with a charge of 2+. And remember to add these state symbols. If you do not include them, they won't give you the mark for this question. Whenever we consider trends in ionization energy, there are 3 very important factors that you always have to consider. And ideally, in your answers, you will mention all 3 of these factors. The first thing that will influence the size of the ionization energy, in other words, how much energy we need to remove the outermost electron or electrons, will be the charge on the nucleus. Okay. Secondly, the distance of the electrons from the nucleus. Okay, so how far those outer electrons from the positive charge. And then the third factor will be the amount of shielding created by the electrons between the outer shell electrons and the nucleus. Okay, so shielding, what does shielding mean? If we have electrons in between the nucleus and the outer electron, so let's say that's the nucleus, this is an electron in the outermost shell. If we have energy levels in between the nucleus and that outer energy level, where we have the outermost electrons, there will be a certain degree of shielding. Okay, so the electrons on the inside will shield the electrons on the outside, from the attraction of the nucleus. So another way to think of it is this outermost electron will be attracted by the nucleus, so it will experience a force towards the nucleus. But because of the inner electrons, it will be repelled in the opposite direction because the negative electrons will repel other negative electrons. So the overall effect will be a decreased attraction experienced by that outermost electron. Okay, so that is the concept of shielding. And the more of these inner shells you have, the higher the degree of shielding and therefore the weaker attraction between the nucleus and the outer electrons. So this slide will just summarize each one of these factors. So nuclear charge is quite self-explanatory. If we have more protons, there's going to be more charge, so a greater positive charge. And if we have a bigger charge, there will be a stronger attraction between the nucleus and the outer shell electrons. And if there is a stronger attraction, we will need more energy to remove that electron and therefore a greater ionization energy. If we increase the distance of the electron from the nucleus, the greater the distance, the weaker the attraction. Okay, the further that electron is removed from the nucleus, the weaker the attraction between the outer shell electrons and the nucleus. And if we have a weaker attraction, we need less energy to remove that electron and therefore smaller ionization energy. And the concept of shielding, so I've explained that when I use this little diagram here. So if we have more energy shells or quantum levels, the outer electrons will experience more shielding, therefore weaker attraction between the outer shell electrons and the nucleus, Weaker attraction means there will be less energy needed to remove an electron and therefore a smaller ionization energy. So for each one of your questions, consider these three factors. Okay, what is the charge on the nucleus? How does that change as we go across a period or down the group? How does the distance and the amount of shielding change as we go across a period or down the group? So that will be repeated again on the next slide as well. Before we get to period 3 specifically, let's just review the general trends as we move across or down the periodic table. So there are two general trends that are very important. The first one is what happens as we go down the group, and then secondly, what happens as you go across the period. And generally, when we discuss the size of ionization energy, the factors that we have to consider will be the distance from the nucleus and the amount of shielding, and then also the nuclear charge. What is the size of the positive charge on the nucleus attracting the electrons? So the general trends going down the group is that the ionization energy will decrease as we go down the group, and that is because the outer electrons will be found in an energy shell which is further from the nucleus. So there will be an increase in the distance between the outer electrons and the nucleus, and as a result of the extra electron shell, there will be more shielding by inner shells, more electrons shielding the outer electrons from the attraction of the nucleus, and therefore the ionization energy decreases as we go down the group. As we go across the period from left to right on the periodic table, we will remove electrons from the same energy shell, so therefore the distance and the amount of shielding will be the same, experienced by the electrons within that shell. But as we go across from left to right, there's going to be an increase in atomic number, therefore an increase in the number of protons. If we have an increased number of protons, there will be a greater positive charge, and therefore the outer electrons will be attracted more strongly by the nucleus. So those are the two general trends. What happens as we go down the group and what happens as we go across the period. So if we summarize all of that, if we use this periodic table to summarize the trends, if we start by looking at the trend across a period, so let's consider period 3, because that's probably the important one here. As we go from sodium to magnesium across all the way to argon, what will be the trend in ionization energy? We know it will increase from left to right, and see if you can explain that by referring to the nuclear charge, the distance from the nucleus, and the amount of shielding. And then the second main trend, as we go down the group, the ionization energy will decrease, or the opposite, as we go up the group, the ionization energy values will increase. Again, try to explain it in terms of the energy shell, where we find the outermost electrons, and then also the effect of that on the distance from the nucleus and the amount of shielding, because that will be the more important factor. Even though as we go down the group, there will be an increase in nuclear charge, but the electrons will be so much further from the nucleus, and there will be so much more shielding that will be the more important of the two factors to consider. Although the focus here will be the trend in the first ionization energy as we go from left to right across period 3, let's just consider a typical question where they show you kind of subsequent ionization energies for the same element. What happens to the size of ionization energy as we go from removing the first electron to the second one to the third, etc. Because if you have that data, and they often give you that as a table, like on this slide, you can use it if it's an unknown element to determine the position on the periodic table in terms of the group where we find that particular element. If we look at a few examples, here we have sodium, and if we look at the size of the magnitude of these values, the amount of energy needed to remove each one of the consecutive electrons, the first ionization energy is 494, and then we jump up to 4560. So there's quite a big jump from first to second ionization energies for sodium, and then there's a relatively steady increase from second to third to fourth. So why is that? You have to consider the electron configuration of sodium and the electrons that we remove. So for sodium, it's in group 1. So when we consider the first ionization energy, we remove the electron from a 3s orbital. If we then go to second ionization energy, we need to remove an electron from a 2p orbital. So we're going to one energy level closer towards the nucleus. So that means that there will be less shielding and there will be a smaller distance between the outer electron and the nucleus. And as a result of that, much more energy needed to remove that second electron. So we can use that if we didn't know that this was sodium. If there's a big jump from first to second ionization energy, it means that this unknown element must have one electron in its outermost shell, because after removing that one, if we want to remove the second one, we need a considerably larger amount of energy. If we look at magnesium, from first to second, okay, there's an increase but not a big jump. If we then go from second to third ionization energy, you can see there's a very big jump in the amount of energy needed to remove that third electron. And if we link that up to electron configuration, the first electron is removed from a 3s orbital. The second electron is also removed from a 3s orbital. Remember, the electron configuration for magnesium ends on 3s2. The third electron removed, okay, we then have to go to energy level or quantum level 2. Okay, so we're moving towards an energy shell closer to the nucleus, and that's where we experience that big jump again. So we can use this information to show that this element, and we know it's magnesium, it's got 2 electrons in its outermost shell. And aluminium, the same trend there. So we have kind of smallish jumps as we go from first to second to third, because we're removing the first one from 3p, okay, then the next two from 3s, and then the fourth electron, if we remove that one, the fourth ionization energy, we need to remove from energy level 2 again, which will be much closer to the nucleus. Stronger attraction, you need much more energy to remove it. So after all of that, how do you use these tables? You look for the big jump in the ionization energy, and where there's a big jump, it shows you that you're now removing an electron from an energy shell closer to the nucleus. Okay, so you can work out how many electrons in the outermost shell of an unknown element. Before we move on, it's probably useful to show it by referring to one of these arrow and box diagrams, or box and arrow diagrams, to show the electron configuration. So this is for aluminium. So to remove the first, second, and third electrons, we remove an electron from the same energy shell. And then to remove the fourth electron, okay, for the fourth ionization energy, then we jump from this energy level 3 to energy level 2, okay, which will be much closer to the nucleus. And that's why we have that big jump, okay, going from third to fourth ionization energies. So you can apply the same thing for sodium and magnesium. Sodium would have 1 electron here in 3s, and magnesium 2. So what are the general trends so far? You'll often get a graph like this one. So if we look at this part on the left here, so the bottom elements will be the elements that we find in group 1 of the periodic table. So all of these elements will be in group 1. And we know all of the noble gases on the far right of the periodic table in group 18. So if we consider the general trend across periods in the periodic table, as we go from left to right, in other words, we go from group 1 to group 18, you can see there's an increase in the ionization energy, as explained on the previous slides. And if we go next period down, okay, the same as we go from the left to the right, from group 1 to group 18, there's an increase in ionization energy. What happens as we go down groups? If we consider group 18, so all of these noble gases are on the same group 18, as we go down the groups, you can see there's a decrease in ionization energy, as expected. For the next part of this video, we need to consider these little anomalous areas where we have a sudden drop and a sudden drop in the ionization energy. So the general trend is, as we go from left to right, Okay, across a period, there should be an increase in ionization energy. So on the next slide, we will just consider in a bit more detail how to explain these areas where we see a drop even though we go from left to right across the same period. So in each one of the periods, this is period 2 going from lithium to neon, and this is period 3 going from sodium to argon, we find these drops in ionization energy at the same positions. In both cases, we find it when we go from the element in group 2 to the element in group 3. Remember, the element in group 3 is also known as group 13. And then we see the same thing happening when we go from the element in group 5 or 15 to the element in group 6 or group 16. The specific elements that we find in those positions on the periodic table will be beryllium to boron for that first part there in period 2, and then the second part here is when we go from nitrogen to oxygen, and then in period 3 it's when we go from magnesium to aluminium, and then we go from phosphorus to sulfur. So how do we explain these drops in ionization energy? To explain these exceptions, you have to consider the electron configuration of the elements in question. So on this slide, we're going to look at magnesium and aluminium specifically, but the same argument will apply when we go from beryllium to boron. So back to the electron configuration, magnesium, we can see the outermost electrons, the valence electrons, found in quantum level 3, or energy shell 3, and the electron configuration is 3s1. In aluminium, we find the 3 valence electrons also in energy level 3, or energy shell 3, but we find 2 electrons in the s orbital, in the 3s orbital, and then 1 electron in the 3p orbital. So when we consider first ionization energy, for aluminium, when we remove the electron, we remove that outermost electron from the 3p orbital, from a p orbital. For the magnesium, we remove that outermost electron from the 3s orbital. So why is it easier to remove an electron from a 3p orbital as compared to a 3s orbital in magnesium? It's because the 3p orbital, being at a higher energy, will be slightly further away from the nucleus. So that's your first explanation, your first point of your explanation. And secondly, there will be a little bit more shielding as a result of the 3s orbitals that we find in aluminium. So because the attraction therefore will be weaker when we consider aluminium between that outermost electron and the nucleus, less energy will be needed to remove that electron, and that's why we have that subsequent drop in the first ionization energy as we go from aluminium to magnesium. So you have to consider where we remove that electron from. So even though it's in the same energy level and there is an increase in the nuclear charge as we move from magnesium to aluminium, because the electron that we remove will be slightly further away from the nucleus, and because there will be slightly more shielding, there will be an overall weaker attraction and therefore less energy needed to remove that electron. There is a different explanation for the exceptions as we go from group 5 to group 16 or group 15 to group 16. Let's consider the electron configuration for nitrogen. You can see here that we have 2 electrons in the 1s orbital, 2 electrons in 2s, and then we have 3 unpaired electrons in the 3 2p orbitals of nitrogen. Oxygen, because there's 1 more electron, the only way that we can put another electron in that energy level is to start pairing up the electrons in the same suborbital, in the same 2p orbital. Okay, so this orbital would be 2px. And if we consider the ionization energies, the energy needed to remove the outermost electron in nitrogen, so one of these, compared to the outermost electron in oxygen, we can see there is a decrease in the ionization energy, even though there's going to be an increase in the nuclear charge as we go from nitrogen to oxygen. So why is that? It's because of a concept known as electron pair repulsion or spin pair repulsion. As soon as we start pairing up electrons in the same p orbital, there's going to be some repulsion experienced. Okay, so this electron here will repel, okay, the other electron in that same orbital. And as a result of that repulsion, the attraction experienced by this electron for the nucleus will be slightly less. Okay, so if there's a weaker attraction, we're going to need less energy to remove that outermost electron. So if you had to explain the exception as we go from group 15 to 16, so either nitrogen to oxygen, or in the case of this chapter specifically, period 13, from phosphorus to sulfur, you would have to mention the specific electron arrangement, that in nitrogen we have all unpaired electrons in the 2p orbitals or subshell. For oxygen, there's going to be a pair of electrons in the same 2p orbital, and as a result of that there's going to be electron pair repulsion and a consequent weaker attraction experienced for the nucleus, and therefore less energy needed to remove that outermost electron. And then the last part of this video, we will look at the concept of ceramics very briefly. And you've all heard of ceramics before, and you probably have a decent idea of where ceramics are used in everyday life. Before we look at the properties of ceramics, you can have a read through this definition. This is the official IUPAC definition, okay, for a ceramic. There's no need to learn or memorize this. All you need to know is the properties of the ceramics, and then also what we use it for as a result of those specific properties. We will start off by considering the bonding and structure within these compounds, which we classify as ceramics. And then because of the bonding and structure, we'll be able to make certain predictions about their properties, okay, specifically their physical properties. So these compounds all have giant structures. Okay, so these giant structures could either be giant ionic structures, okay, but also giant covalent. And whenever we have these giant ionic and giant covalent structures, we have very strong bonds between all of the atoms or the ions within that structure. Remember, a giant structure contains billions of ions or billions of atoms, depending on whether it's giant ionic or giant covalent. And if you wanted to melt one of these structures, you would need an enormous amount of energy to break all of those strong bonds, all of the strong ionic, okay, and covalent bonds. If we consider a giant molecular structure like ice or iodine, we only have weak van der Waals forces between the molecules within that structure, and therefore they will boil or melt at quite low temperatures. But for giant structures, you're going to have to break strong ionic or covalent bonds. And as a result of these strong bonds within these giant structures, all ceramics are described as hard and strong materials, but they are also brittle. And because of the strong bonds, ceramics have very high melting points. So you need a lot of energy to break all of those strong bonds within the structure. Most ceramics are good electrical insulators. That means they do not conduct electricity. Why not? Because we do not have any delocalized or free electrons to move around within these giant structures. And even if it's a giant ionic structure, the ions are held in place, okay, in that solid lattice. It's only when we melt or dissolve ionic substances that they are able to conduct. Okay, so therefore ceramics are good electrical insulators, okay, and they're also good heat insulators. They do not conduct heat well. Some examples that you need to be aware of, and it's important to learn these three examples. Okay, we have aluminium oxide, silicon dioxide, and magnesium oxide. Okay, magnesium oxide has got a giant ionic structure. Silicon dioxide we know is giant covalent. Aluminium oxide is also a giant covalent structure, but it does have a degree of ionic character as well. Because of these typical properties of ceramics, one of their main uses is to line areas that experience very high temperatures. One example of that would be a furnace or a kiln. And a substance that can withstand a very high temperature, like these ceramics, are known as refractory materials. So that's just a term to take note of. You might encounter it going forward. I think we have come across that term in some of the previous sections as well. But a refractory material, a material that can withstand very high temperatures, like the ceramics, okay, without losing their properties. Which statements about ceramics are correct? Ceramics are good electrical conductors. So we know that is incorrect, because in the giant ionic and giant covalent structures we have of the ceramics, we have no free electrons, and the ions cannot move, therefore they cannot conduct electricity. Ceramics are strong materials, yes, because of their giant structures and the strong ionic and covalent bonds. They are strong materials, and they have melting points. Again, for the same reason, that is also correct. So 2 and 3, I think that is option B. Cerium 4 oxide is a ceramic. Suggests 2 physical properties of cerium 4 oxide. And you can give any of the following options as your answer. We know they have high melting or boiling points. They are electrical or thermal insulators. They are hard or rigid structures, and they retain strength even at very high temperatures or pressures. The diagram below shows the first ionization energies of the first 18 elements of the periodic table as we know it today. Give the equation including state symbols for the first ionization energy of fluorine. So as we stated earlier, these state symbols are very important because as per the definition, it's the energy needed to remove 1 mole of electrons from 1 mole of atoms or ions, but these atoms or ions must be in the gas phase. And for the first ionization energy, it means that we still start with a neutral atom. So we'll start with fluorine atoms in the gas phase. After removing 1 electron, we will have a fluorine ion with a 1 plus charge. Ions will also be in the gas phase, and you have to show that we have removed 1 electron. Explain why there is a general increase in the first ionization energies from sodium to argon. So looking here from sodium to argon, so that will be across period 3. So the ionization energies and the factors in influencing ionization energy to be considered will be nuclear charge, okay, the shell where we find the outermost electron, and therefore the distance, okay, or the shielding involved as well. So as we go from sodium to argon, we know that the electrons are added to the same shell, so they will be the same amount of shielding experienced. But as we go from sodium to argon, there's going to be an increase in the number of protons, okay, and therefore an increase in the nuclear charge. So as we go from sodium to argon, there would be a stronger attraction between the outermost electrons and the nucleus. Explain why the first ionization energy of aluminium is less than that of magnesium. So this is the first one of those exceptions which we looked at as we go across a period. So aluminium is in group 3 or 13, and magnesium is in group 2. So as we go from group 2 to group 3, why do we see that little dip in the ionization energy? So we explain it by looking at the electron arrangement of these atoms. Okay, so your answer will have to mention that in aluminium, the outermost electron is in a 3p orbital rather than 3s, and being in 3p, the electron will be at a higher energy level, therefore is slightly further away from the nucleus and is also more shielded from the nucleus. Explain why the first ionization energy of sulfur is less than that of phosphorus. So this is that second exception as we go across the period, where we have sulfur in group 16 and phosphorus in group 15. So how do we explain that the dip in ionization energy as we go from group 15 to group 16? Again, we have to consider the electron arrangement, but for this exception, it will be because in sulfur we start pairing up the electrons in that p sublevel. There's going to be one p orbital where we have a pair of electrons, and as a result of the electron pair repulsion or spin pair repulsion, we're going to have a weaker attraction between the outermost electron and the nucleus. The graph below shows the variation of the first ionization energy with the number of protons for some elements. Which statement is correct? Elements Q and Y are in the same period in the periodic table, and we know that is not correct because the trend that we see across a period is an increase in ionization energy. So this would be elements in the same period. So that is not a correct option. The general increase from elements R to Y is due to increasing atomic radius. So as we go from R to Y, there's an increase in first ionization energy. That is correct, but it's definitely not as a result of increasing atomic radius, because we know the atomic radius actually decreases as we go across a period. That is not correct either. The small decrease between S and T is due to decreased shielding. So from S to T, as we go from an element with electrons only in an S orbital to a P sublevel, there's actually increased shielding. Okay, so that is not correct either. The small decrease between V and W is due to repulsion between paired electrons. So that's there, V to W, where we go from group 15 to group 16, and we know that is the correct answer because we have one of the p orbitals in that sublevel with a pair of electrons, so we have spin pair or electron pair repulsion. The first ionization energies of 20 successive elements in the periodic table are represented in the graph. The letters given are not the normal symbols of these elements. Which statements about this graph are correct? Elements B, J, and R are in group 0 of the periodic table. So we're looking at B, J, and R. Group 0 is also known as group 8 or group 18. And we know those are the noble gases. As we go up each period, they've got the highest ionization energies as a result of the increase in the nuclear charge. So that is correct, option 1. Elements D and L contain 2 electrons in their outer shells. So D is that one and L is that one. That's also correct because as we go here, this element here will have only 1 electron in its outer shell. So as we go drop down from there to there, we know it's because we're going into a next energy shell or energy level. So this is the first electron, second electron. And we also know that we have this little dip because we then go into the P sublevel. So this would be 2 electrons in the S sublevel. Same here, 1, 2. So that is also correct. And then elements G and O contain a half-filled P subshell. So G and O. So a half-filled P subshell, so that would be 3 electrons in the P orbitals. And we also know that's correct because as soon as we go beyond that, where we have to add a 4th electron to that P subshell, we get to kind of a paired P orbital, and as a result of the electron pair repulsion, we see that will decrease in the ionization energy. So 3 is also a correct option. So all 3 options correct. Element X forms X minus ions that can be oxidized to element X by acidified potassium manganate. So from that information, the guidance there is probably hinting towards the fact that this element X must be in group 7 or group 17, because we know that they have 7 electrons in the outer shell and they need 1 more to get a full outer shell, and when they gain 1 electron they will form ions with a charge of 1 minus. So we're probably looking for an element that is in group 7 or group 17 of the periodic table. What could be the values of the first 4 ionization energies of X? So if we look at the options A, and they give us consecutive ionization energies, we can see there's a big jump here as we go from the first to the second ionization energy. What does that tell us? It indicates that that element A is probably, or not probably, is in group 1 of the periodic table. For option B, we can see the significant jump is from the third to the fourth ionization energy. So we know that that element is in group 3 or group 13 of the periodic table. We're going to remove the first 3 electrons quite easily, and then we need much more energy to remove the fourth one, because it will be in an energy level or an energy shell closer to the nucleus. So this, if we just write, so this is something in group 1, group 3 or group 13. If we look at option C, okay, so here we can see there's a big jump from the second to the third energy level. So this is probably an element in group 2. So we're looking for something in group 7 or group 17. So we don't want to see any significant jumps within the first 4 ionization energy values. And if we look at option D, okay, you can see there's no big jump there. So that means that that's our only option. So D must be the correct answer. They also do specify that the use of the data booklet is relevant. So if you're not sure whether there is a big jump, for example, for option C, do you think the big jump is from 2 to 3 or from 3 to 4? If you're not sure, you can use the data booklet where they show you the ionization energies, and you can identify specific elements that way as well. If you do that, you'll find that the ionization energies given in option A is actually for the element potassium, which is in group 1, as we expect. B is for aluminium, and that is also in group 3 or 13. C is calcium, and D is actually for the element iodine, which is in group 17. So it will form an ion with a charge of 1 minus. So the correct answer there, D. The elements radon, francium, and radium have proton numbers 86, 87, and 88 respectively. So there's an increase in the number of protons and therefore an increase in the nuclear charge. But to answer this question, and they do say that the use of the data booklet is relevant, and you should have a periodic table in front of you when you answer this question. So if we just add symbols here so we know which ones we're referring to. So this would be the radon, then francium, and then radium. If you look at the periodic table, you'll see that we have radon, and then we drop down to the next period for francium and radium. So they in the next energy level. So their outermost electron will be further away from the nucleus compared to radon. So radon will require the most energy to remove its outermost electron, and therefore will have the most endothermic first ionization energy. Remember, we need energy, we require energy to remove these electrons. It's all endothermic values. We need the most energy for radon because it's in a higher period in the periodic table, so therefore we one energy shell in compared to the other two elements. So smaller distance, stronger attraction, so more endothermic values. So far we can look at those two options, A and C. If we then go to the next period, these have their outermost electrons in the same energy shell, so generally the same amount of shielding experienced by their outermost electrons. But as we go from left to right, there's an increase in the number of protons, therefore an increase in the nuclear charge, therefore a stronger attraction if we have more protons, okay, for the outermost electrons, therefore a more endothermic value. So these two, the trend will be from francium to radium would be the increase in the endothermic value. So that must be this one, francium to radium. A is the correct answer. Equations involving 4 enthalpy changes are shown. What is the second ionization energy of sodium? So second ionization energy of sodium, if you had to write it as an equation, would be the removal of 1 mole of electrons from 1 mole of sodium 1 plus ions. So these ions must be in the gas phase, and when we remove another electron from that sodium ion, we would form an Na2 plus ion plus another electron. So you wouldn't find an equation up here to match this particular enthalpy change. So you're going to have to look at a combination of two of those, which we can use to work out the value for this enthalpy change. So if we look at the second one, that would be going from a sodium atom to a sodium 2 plus ion plus 2 electrons. So that would be removing the two outermost electrons. Okay, so that's not what we're looking for. We only want the energy needed to remove not the first electron, but the second one. So this is the energy needed to remove both of the two outermost electrons. The first one is the energy needed to remove only the outermost electron. So if we take the difference between those two values, okay, so X is the energy needed to remove the first electron and the second electron. If we take X minus the energy needed to remove the first electron, we will end up with the energy value needed to remove the second electron only. So X minus W is the correct answer. That is B. This is a last exercise, just a few true or false questions. Okay, not really a past paper question. The first question, elements 2, 10, and 18. Elements 2, 10, and 18 are in group 1 of the periodic table. Okay, so we know they're in the same group in the periodic table, but definitely not group 1. They're all the noble gases. Okay, we can see we find them kind of at the end of each one of the periods. As you follow the trend across the period, we know there's an increase in the ionization energy. So they'll all be in group 18 or group 8 or group 0 of the periodic table. So question or option number 1 there is false. Atoms of elements 4 and 12 have only 2 electrons in the outer shell. So this is similar to one that we've had previously. So we're looking at elements 4 and 12. So 1, 2, 3, 4. Okay, so that one there, and 12. 2 electrons in the outer shells. That is correct, because they have 1 electron in s orbital and then a second one for each one of those. So that is true. And elements 7 and 15 have half-filled p orbitals. Okay, sorry, this is exactly the same as the previous question. So this one and this one. Half-filled, yes, they've got 3 electrons each in the p subshell. And then as we add a fourth one, okay, we have the electron pair repulsion, and therefore that subsequent decrease in the ionization energy. So that is also true.